Good morning. So my talk is about circuit design with process variation. It's a good start. So this is a short introduction by myself. I'm a design engineer with analog devices, where I work mainly on precision A to D converters, especially sigma delta. And I'm also serving as an associate editor for the transactional circuits and systems one. And I'm also part of the technical program committee of ISSCC for converters. This is just an overview of analog devices. Analog Devices is a global semiconductor company with a wide spread of technologies, and is present in 31 countries across the globe. And we have about 24 people working in ADI, and more than half of them are engineers. So there's a lot of R&D being done in ADI. So this is the outline of my talk. We are going to look at process variation. There are essentially two types of process variations, and we are going to see techniques to deal with these two types of process variation. Okay, so let's start with some definition. We can really group the process variation in two types. The first one is inter-die or chip-to-chip variation. And this basically refers to all the variation which are common for devices on the same die. And then we have a second group of variation, and this basically is about the variation that you observe for devices which are sitting on the same chip. So let's start with the inter-die variation. When you manufacture a chip, you'll find that you see a great variation of the parameters from one die to another die. The range is typically in the tens of percent, so that's quite large. But the good news is that this type of variation is well characterized by the foundries, so you get process libraries and you can simulate that quite accurately. And the usual way to deal with this sort of variation is very simple. Typically, you implement circuits which are ratiometric, so where the transfer function is defined by the ratio of components. And therefore, if the components vary by the same percentage, the transfer function doesn't change. So here we have a simple example of an inverting amplifier, where if the Rin and RF change by the same percentage, the gain doesn't change. This is another example. This is a capacitive DAC. This is kind of the equivalent of the resistive DAC that Ali just showed previously. You can look at this just as a divider. And again, if all the capacitors change by the same percentage, the transfer function of your DAC doesn't change. So once you have a DAC, you can also build an ADC. And the simplest way, I believe, is to put that DAC into a SAR loop. So you need to add a comparator, you need to add a SAR engine, and then the SAR engine can basically drive the DAC and find the value from the DAC, which is the closest approximation to your input voltage. And you do that by using the SAR routine, and the SAR routine is really just a simple binary search, a bisection method. So here we have an example for the 4-bit A to D. So let's imagine that our input is sitting here just above VRF over 2. To find the closest approximation, what you do, you halve the search space, right? So you start by halving the entire search space into halves. So you set the threshold at VREF over 2. So you set the first bit in your DAC to 1, and you compare where your input is sitting compared to this threshold. So here the input is above, so it means that our input is sitting in the higher half search space. So we select that. We keep the bit to 1, and we move to the next search space. So again, we divide it by 2 by setting the next bit to 1. So this again halves the search space. It sets the threshold to 3/4 of VRF. And we do the comparison. Here we find that it is below. So we don't keep that bit. We set it to 0. And we move on like that. So we always halve, and we keep going till we get all the bits. And once you've finished, you are left with a residual error. We call this residual error the quantization error. And it's essentially the difference between your DAC at the end of the conversion and the input. And when you're sitting exactly on a threshold, this error goes to 0. But if you're not sitting on a threshold, as you move away, the error grows, and you get this characteristic sawtooth type of waveform. So, ratiometric circuits are great. They work very well. You need to pay attention to parasitics. And typically, the way we take care of parasitics is by either making the contribution from the parasitic ratiometric as well, or by using circuit techniques that make the contribution of the parasitic negligible. So again, if you look at our very simple example of an inverting amplifier, if you want a gain of 1, you have to make the feedback and the input resistor the same, but you also have to make the parasitic track resistance, RFP and RINP, the same to keep the gain at 1. Or you can use circuit techniques. And here, for instance, because this is an operational amplifier, there is no current, so this parasitic track resistance doesn't matter. So let's look at, I guess, maybe a more interesting example of how to make parasitic negligible in the case of a CDAC-based SAR converter. So if we take the one that we've been looking at, and we consider this node, what we'll find in practice is that we have nonlinear capacitances hanging on that node. And this is because, for instance, this switch will be made with a MOS device, so you have diode junction capacitance. And if you do your simulation, you'll find that this node here is not linear with the DAC code. You'll have some nonlinearity. And as you go to higher accuracy, 4-bit is probably fine, but if you go to higher accuracy, eventually you'll find that this is an issue. So how can we deal with that? There is a much better implementation of a CDAC-based SAR ADC, and it is shown in this slide. So the difference compared to the previous one is that here we start by sampling the input on all the CDAC capacitors. So you see, we introduce an acquisition phase where we apply the input to the bottom plates of the CDAC, to all of them, and we drive the top plate to 0, to ground. So during this acquisition phase, we apply the input across the entire CDAC, and when the acquisition signal goes down and we open the switches, this voltage is captured across these capacitors. And then you move to the search bit trial phase, and you connect your CDAC to your reference, and you start the MSB trial. And if you use charge conservation, you'll find that now this node, the voltage on this node is given by this expression here. Ignore the parasitic capacitance for the time being. So you'll see that it's given by the DAC code scaled by VRF minus the input value that you have sampled. So again, you can do the SAR search routine by looking at the polarity of this node. And I think this explains why now if you add a parasitic capacitance which is nonlinear on this node, it doesn't matter, because the only thing that you really care is the polarity of that voltage, right? So even if the voltage is nonlinear, but as long as the sign is the same, you're fine. Another way to look at it is that during acquisition, this switch was turned on, and you had a 0 voltage across this capacitance, okay? Now, when you do your search bit trial, and you're doing a critical decision, by critical I mean that the difference between the DAC code and the input is very close, okay? What happens is that, again, this node goes back to 0. So that means that the voltage on CP is again 0. It means that you're back to the original situation. This capacitor hasn't delivered or absorbed any charge from this node, okay? So again, it doesn't matter. During a critical decision, it doesn't matter. And this allows you to get very, very high accuracy. Okay, so that's all I had on inter-die variation. And we can now move to the intra-die variation. So here we are talking about the variation that you observe between elements on the same chip. And there are many reasons why these elements are not the same. This can be due to manufacturing, thermal gradients. Maybe you have a big LDO that's sinking or sourcing a lot of power in a corner of the die. Or because if you have mechanical stress, again, maybe your devices are close to a corner in the chip, and you have random. So let's start to look at those. And clearly, if you want to make devices match, the first thing that you want to do is to try to make them identical. In theory, you should look at them, and you should not be able to tell which one is which, right? Just by looking at them. So that means that clearly you have to use exactly the same type of material, same form, same orientation, same dimensions. And you also have to make the surrounding the same. They should look at the same surrounding. So this means that typically you have to use dummies around the devices that you want to match. And you also have to be careful about these filling patterns. So in low geometry processes, there are some uniformity rules that you have to meet. And to do that, there are some automatic routines that generate filling patterns that basically generate these patterns so that rule is met. Unfortunately, if you look at those patterns, they don't necessarily guarantee that the surrounding of the elements that you want to match is the same. So you have to look at those, and in most cases, you have to do these filling patterns by hand yourself to guarantee that the surrounding is the same for the devices that you want to match. Even if you do great layout and you observe all those rules, you'll typically find that the parameters of a device will still depend typically on the position of that device on your die. So for instance, here we have a simple example of an array of resistors, and you may have that you may find that the resistivity of the resistor is changing linearly across the array of your resistors. So if you want to implement an amplifier with a gain of -2, you find that basically the resistor on the left is always a bit smaller than the resistor on the right. So if you choose the feedback resistor, you make it by splitting it in two, and you place the feedback resistor around the input resistor, you'll find that this gradient cancels, right? So this is a very simple example of a first-order cancellation gradient scheme.
So what is the x-axis? What is the x-axis?
How do you mean?
X-axis is a distance.
It's the distance. It's just the distance. So this is kind of your layout, and this is just the distance of the resistor. So there are schemes which are much more involved and can take care of higher order gradients, and they work quite nicely. Just one word of caution: you have to look at the complexity of the routing that is associated with this type of schemes, and consider that when you do your design. So even if you take care of the gradients, you've done great layout, at the end of the day, you're still left with random mismatch, right? So if you look at a parameter of a device, you'll find that the standard deviation of this parameter typically goes with the 1 over the square root of the area, just because of this random mismatch which is left. And so clearly you can make the area bigger, but that's not always possible, either because just cost or because the parasitic may become too large. So at the end of the day, you have to come up with schemes to correct for these errors. And the first technique that comes to mind is calibration. Calibration is conceptually very simple. So imagine you have an A2D, and because of mismatch, there is some error introduced. What calibration does, it just injects the opposite of that error. You come up with an estimate of this error, and you simply subtract that estimate. It's as simple as that. You can implement it in the analog domain, or you can implement it in the digital domain, and you can do it either at factory when you're producing the part, or you can have some circuit that powers up, runs the calibration algorithm, and finds the calibration coefficient that needs to be introduced. And in this case, we talk about foreground calibration, when you do the calibration before operating the circuit. There are other schemes where the calibration is running continuously during the operation of the circuit itself, and in this case, we talk about background calibration. So if we go back to our CDAC SAR ADC that we've seen before, this is an example of an analog calibrated CDAC SAR, where we have a trim DAC, which is in parallel with the main DAC, and we store basically the calibration coefficient in a ROM, and we inject them at the output of the CDAC. So that's a simple example of analog calibration. Similarly, you can do digital calibration, and in this case, you basically have the correction at the output in the digital domain. So calibration is great, but it has some costs associated because you have to add extra circuitry, you have to store the coefficients somehow. So people have been thinking about schemes that could get away without running this calibration, and certainly in the past, delta sigma is being used for this. So delta sigma converters can be used to implement both analog to digital converters, and we have an example here on the left. And they can also be used to implement D2A, and we have here an example on the right. Just to get you a basic idea of how a sigma delta works, the basic idea is that you take a quantizer with very, very low resolution, and you put that in a feedback loop, and you increase the accuracy by exploiting the feedback action of the loop. So if you use this very simple model and you derive the transfer function, you'll find that your output is given by the signal transfer function times x, where x is our input. And then we have a second term which is caused by the quantization error, which gets multiplied by the noise transfer function NTF. And if you look at the expression for this signal noise transfer function, if you can keep the loop stable, that's important, but we don't have time to go into that. But if you can make it stable, and if you have a lot of gain in the bandwidth of interest, what happens is that the STF is close to 1, so your signal just goes straight through, and the quantization error on the other hand, is heavily attenuated. So that's really just the basic idea that we use in sigma delta. And you can really push things to the extremes in terms of resolution of the quantizer, and you can go down to one single bit. So single bit is great for the fact that there are only two levels. There is only one line through two levels, so that's linear. And people have implemented converters without 1 ppm linearity using single bit DACs, and without calibration or any particularly fancy device. So this is an example of a spectrum of a single bit second order sigma delta. So here you can see that this is our input tone that's coming out of the modulator, and you can see that at low frequency there is very little noise content, and then it grows as we move away from the band, from DC, which is our bandwidth of interest here. Single bit sigma delta have been used and done, and they work nicely, but as you can see, you have a lot of quantization error. You can imagine you just have 1 bit of quantization, right? So you really need to have room in your spectrum to push that noise away from your signal bandwidth of interest, sorry. So that means that typically you end up running with a pretty high sampling frequency, and this means burning power. So there are a number of reasons why, and especially power, I would say, that have pushed people to move away from single bit modulators and start to think about using multi-bit. And now again, you have the problem that the DAC might not be linear. You have to deal with a mismatch error. So I think this is really how these dynamic element matching schemes were started to be looked at as an alternative to calibration again. So dynamic element matching is really, again, another way to implement accurate DACs without recurring to calibration. And we can really group them into two types. There are scrambling DEM, where the basic idea is that you take your mismatch error and you turn that into noise, and you spread that uniformly across your Nyquist band. And then there are shaping DEM, which are more akin to sigma delta, where you try to shape that noise as well. So you try to push it away from the bandwidth of interest. So let's start with the simplest multi-bit DAC, which is just a 2-element DAC. So we have the 2 elements, we add them together, and here is the transfer function that we expect from an ideal 2-element DAC. So we have 3 possible input codes, 0, 1, 2. At 0, we don't select any elements. The output is 0. At 1, we select 1, and we get an ideal weight of WI because the DAC is ideal. And then here we get 2. So all these points sit on a straight line. The DAC is linear. Everything is good in an ideal world. In the real world, you'll get mismatch. So what happens there? So let's define E1 as the mismatch error of the first element and E2 the mismatch error of the second element. And now let's see what happens. So at 0, again, no element selected, we get 0. That's good. At 2, if we define this average weight, we end up really with 2x the average weight. And that's fine. The problem is then for the midpoint at code 1, where we're actually free to select either the element 1 or element 2, but we never sit on this line if there are errors. But what we can observe is that the error that we get with selecting one element or selecting the other are symmetric around the points that we'd really like to implement. So that means that on average, we can actually implement that value. So the idea is that if on average you select one element, on average, sorry, you select both elements equally, right? Then the average value for a code of 1 will be sitting exactly there. That's the idea of the scrambling DM. And here we can see a sigma delta modulator, again, the second order one that we've seen previously with just a single bit. So here we have used the 2-element DAC, and we also introduce a mismatch error between the 2 elements of 0.001 with an average weight of 1. And the red curve is the ideal one, and the green one is what you get with this scrambling DM. So you can see that, okay, it tracks here, and then eventually it flattens in this region. And in this region, what happens is that we get this mismatch error, which has been turned into noise. So it's this mismatch noise in blue. And as you can see, it is spread uniformly across the entire Nyquist band. So that's the scrambling DM. But you can actually do better, and you can shape this noise. You can do better, at least in an oversampling scenario. And you can shape it. And this is a simple scheme. This slide describes a simple scheme to shape that error. So the basic idea is that you want to keep the running sum of those errors bounded. Okay. And really, we've seen that the error is only introduced when the input code is 1, right? So that's the only case that we really have to consider. Now, how do you keep the running sum of the errors bounded? It's quite simple. So if you see that the sum of the errors previously was giving E, you can select the second element and inject an error of -E, so that brings it back to 0. Vice versa, if it was -E, you select the other element, and that injects a +E error, and again brings it back to 0. If the running sum was 0, then you're free to select any of them. So if you implement these schemes, what happens is that then the sum of all your error is going to be always less than E, and this means that basically at DC there is 0 power. So if you think about this, is basically the FFT of your input, just run for m samples, and this means that even if you increase the number of samples, the total energy kind of stays constant. So that means that the power keeps decreasing as you increase the number of samples on which you integrate, on which you look. So you end up with a shaped noise, and we can see this in simulation. So again, I've taken the same second order 2-element DAC that we had before, but now I use this scheme, and notice that I've increased the error by 10x here, and in spite of that, you can see that the noise is lower than what we had before, thanks to the shaping that is being introduced by this scheme. So that's really the core idea of most of this DEM scheme, is that if you sum all the errors, you end up to 0. So they all exploit this property. Basically, you try to use, on average, the elements equally. That's really the key. And people have extended the schemes to more than 2 elements. They implemented high-order shaping, bandpass shaping, and they also extended them to segmented DACs. So by this I mean DACs where the weights of the elements are not all the same, and in particularly binary DACs, binary weighted DACs. Just as an example of what you can do, if you're really looking for the ultimate type of performance, typically you end up combining both calibration and dynamic element matching schemes. And here we can see that, for instance, here we have a SAR ADC from analog devices, and the INL error of this SAR is less than 0.1 ppm, and this is a data sheet plot, so this is achieved in production. So you can really do quite impressive things combining this dynamic element matching techniques and calibration. So, in conclusion, so we've seen that when you fabricate chips, your components will be subjected to process variation, both inter-die and intra-die. But we have come up with a number of techniques to deal with them, and we have demonstrated that we can get better than 0.1 ppm accuracy in production using these techniques. And clearly, to achieve this sort of accuracy, you need a combination of techniques. So it is quite a holistic kind of view of what the circuit does. And there are things where I didn't have the time to go into, but there are things like packaging also you need to be careful. There are a lot of subtle effects that you need to take into consideration. And I would expect that because the process variation is not going away by any means, and I think it's getting worse and worse as we go to lower geometry nodes, that we will see more investigation of techniques to get around these issues. And that's really all I have.